Good afternoon to everyone. Our next speaker is Dr. Devendra Kumar Misra. He has completed his BSc, MSc and DPhil from University of Allahabad. Dr. Misra received a lot of academic awards like NET Lectureship Qualified Award, Slovak Academy of Science Award, UGC Research Award, Non-MOU Fellowship Award Japan, Visiting Fellowship Award Japan, Raman Fellowship Award. Currently, he is working as Associate Professor, Department of Physics, Institute of Science and Technology, Banaras Hindu University. He is going to deliver a lecture on challenges associated with quantum sensing system. Now, I would like to invite Dr. Sonam Jain to present a plan to sir. Okay, the lecture will going to start now.
Thank you very much. Good afternoon to all of you. Let us discuss the introductory way about the quantum sensing with optical fields. Okay. So question is that why we are studying, why we are focused, why we are running behind these things. We can see here a lot of investment in quantum technology around the world from different countries, different companies. You can see, and you can also see the investment from different countries in this area. And this is the global startup heat map for the quantum technology. So my focus is to study about discuss about the quantum sensing. Let us start with a brief introduction about the quantum optics or optical fields. Some students asked about some nice questions. There are some terms which we must learn before to proceed this kind of thing. So terms are classical and non-classical. What is quantum and what is classical? What is classical and what is non-classical? In our sense, classical, we know classical mechanics, where we have done all things very precisely, and they don't know about the Heisenberg principle and other things. As we shrink the size of our system, going to atomic level, then the role of quantum mechanics will emerge. And at that position, the Planck's constant will have a role, and also the quantum mechanical theories like Heisenberg principle will also play the role. And first of all, you can see what is the quantum sensing, and in quantum sensing, what are the different areas? You can see from this is visible or not? Not visible. There is a huge area in quantum sensing. You can sense gas, you can sense smell, you can sense position, you can use the GPS technique to locate the position, you can sense the gravitational wave, you can sense the tumor in your brain, or you can sense the cancerous cells in your body. So there are many things you can sense. So what is the problem with current area or available technique? You have images when you go to the medical diagnostic centers, and you have image. That image have some limitation, and as we are thirst of precision by nature, humankind is thirst of precision. You can see from your childhood that your precision is going up to the mark, and as we will grow and later, then we need more and more precision. Okay, so in our daily life, that precision is not so important, but at the experimental level or observational level, where we need the quantities up to the mark, then we need the precision limits beyond available techniques. For example, if we are trying to locate an object on the earth at this position from the space by using space satellite, then the image quality is important, and that importance can be enhanced by exploiting the properties of quantum mechanics. How we can enhance that sensitivity, we can study here. There are different kind of quantum sensing techniques. Our focus is the optical regime. We will use quantum optics, and using that we will use interferometric techniques to enhance the sensitivity of our devices. Do you know any interferometric techniques in your classrooms? Did you study it at this moment? No, I think no. ना? इसमें से कितने लोग बीटेक एक्सट्रीम के हैं, कितने लोग बीएससी बेसिक साइंस के हैं? सब all students are you are BSc, and all of you are BTech. So I assume that, not assume, I am sure that all of you have done your intermediate with physics. Okay, so and your answer is no, you did not study about the interferometer up to this time. Okay, yes, and I am saying that you have studied. So do you know about the Michelson-Morley experiment? What is this? Michelson, just don't worry. You don't worry to say any precise answer, but just interact. So all of you are well aware about the Michelson interferometer, Michelson-Morley experiment, and in that Michelson-Morley used the Michelson interferometer. And what was the result? What was the important? Why we are studying that experiment until this time? What was the importance? Importance is Michelson-Morley experiment negated the concept of ether. Ether, okay? याद आया? ठीक. So ether, and that is a famous negative result of our scientific history. Do you know any other negative result? No. If you have any negative result in your experiment, you simply discard that. But Michelson-Morley did the experiment in around 1887. Okay, and that experiment negated the concept of ether. That was the famous result. And using that also, Michelson interferometer, we do the experiments to calculate that, to observe the difference between two wavelengths of sodium light. Okay, am I correct? D1, D2 lines, and we have a result. Suppose that this is okay. So Michelson interferometer is, am I able? Michelson interferometer is very simple block diagram. This is a beam splitter. As the name is, beam splitter divides the signal. Okay, so this is beam splitter, and here we have a source, light source, and beam splitter, as its nature, divides the signal into two parts. Okay, and here we have a mirror. This is mirror M1, and this is mirror M2. Okay, please tell me when time comes 3:40. Okay. 3:40. So this is, we have two signals. These arms are and after reflection we have a signal here and this is I means our observation. Okay, and after observation we have some kind of interference pattern, and using that interference pattern we calculate the separation between two lines of sodium light. Okay, and this is, now question is here, when we will get the phenomenon is that when this radiation, suppose this is number one, okay, this is divided into part 2 and part 3. Okay, now after reflection from M1, this beam is 4, and from this mirror the reflected beam is suppose 5. This is 5, and 4 and 5 here the beam reflects here. This is suppose 6, and this beam transmits from beam splitter, and we have 7. These two beams 6 and 7 will superpose with each other to produce the interference pattern. So they are in phase. Question is that what is the condition for observing the interference pattern? Suppose distance from this beam splitter to mirror M2 is X, and distance of this beam splitter to M1 is suppose X1. The condition is that these two distances must not be equal. So in practice, one of this mirror is movable from up and down. As we get this X, delta X equal to X1 minus X2 is not equal to 0, then we will observe a very beautiful pattern. Do you remember or not? आप लोग ये गूगल में जा करके देखिएगा, ये माइकलसन इंटरफेरोमीटर का जो फ्रिंज पैटर्न है, वो सपोज दिस इज ए सेंटर पॉइंट, and then we will observe concentric rings, and this is very beautiful experiment. अभी मत देखिए, अभी थोड़ा हमें सुनिए, ठीक है? तो नोट कर लीजिए. तो if you see and if you move this mirror, any one of mirror, to change the distance, and you will observe that many fringes will evolve from this center point or will extend at that center point. That is very amazing experiment. So my task is to know the difference between these two wavelengths, D1, D2 lines of sodium radiation. Okay, that is very good experiment with high precision in our classrooms. But as soon as we need more precision in this experiment to know, suppose we have like ये कितना आता है किसी को याद है डेल्टा लैम्डा नहीं आता. Suppose this is like this, we report. Then our need is to know the precision of this measurement, this experiment, up to, suppose this is 10 place decimal. Then this experiment with our conventional laboratory apparatus will not be able to do this experiment to find the precision up to 10, 20 places. Question is, why we need such kind of observation? In advanced level experiments or devices, we need such kind of observations or results. This kind of experiment is like a sensor, and this is optical sensor to find the difference between two wavelengths. And here we are using only classical optics, following geometrical optics, polarization, interference, diffraction. Okay. When we will require such kind of observation, then we cannot observe such kind of observation by using this setup. Then what is the remedy? No remedy. Okay. Another question is, can we go beyond the, suppose, can we find the image quality more precise as compared to that available in our mobile or more advanced camera? Answer is no. And also answer is yes. Answer is yes. How we can go beyond the maximum precise or maximum quality of image which is available at this moment? Answer is yes, but we will discuss gradually. So our focus is this quantum sensing area is very broad, and I will focus here. We are focused here. In this, we are using interferometric techniques by using optical field. Okay. So if you see here and this image, you can see that this apparatus is extension of this kind. Just extend this, and here we can put a second beam splitter, and then here our detection instrument. What is the change? Change is, we have now, in this setup, we have now two inputs. In Michelson interferometer, we had only one input and one output. Here we have two input and two output. Okay, so that can be used to study more precise experiments or observations in laboratory. This is going more detailed. What is do you know about second quantization? Do you remember? Just a simple way, we can our radiation light source is of dual nature. This is particle nature as well as wave nature. So if we enter in, if we quantize our radiation, or if we consider wave nature of our electromagnetic radiation, then here we have electric field as well as magnetic field. Okay, and this can be used to write 4 Maxwell equations. 4 or 5? There are 5 Maxwell equations or 4? 4. Okay. So we have 4 Maxwell equations for which relation? 4 Maxwell equations are क्या क्या उसमें है बताइए, किसके किसके बीच वो रिलेशन वो बताता है? इलेक्ट्रिक फील्ड, we have electric field and magnetic field, and relation between these two electric vector and electric field vector and magnetic field vector is formulated by the 4 Maxwell equations, and this depicts the travel of transmission of electric field or magnetic field in the medium, and how we can get electric field vector by using magnetic field vector, as well as how we can get knowledge about the magnetic field vector by using the electric field vector. So your task is to memorize, to know about the Maxwell equations, 4 Maxwell equations, relation between electric field and magnetic field. If you don't know about this, then you will have trouble to learn about the other things which we will discuss further. So I will write simplest equations to depict the analysis. Okay. Suppose we have electric field this and magnetic field this. Question, another question, right? Why we discuss in textbooks about the only electric field, focused on electric field, why we don't care about the magnetic field. However, you can know the expression of magnetic field by knowing the electric field vector. So this is very simple question. Suppose this is form of, this is E0 cos omega t, or right, suppose this is, we write e power I omega t plus e, suppose this is E1 and this is E2 and e power minus I omega t. Suppose, for example, this, and if we quantize this radiation, electric field vector, so that we can write E. Now this is, if we write in quantized form, then we will denote it by a cap, putting a cap on this. Okay. Or we can write here, this is A e power I omega t. There is some space coordinate also, and plus A dagger. Do you know A dagger or A? I minus I omega t minus kz. Okay, this is you can get this like expressions in any textbook of quantum optics. For example, you can get the book of Agarwal, G.S. Agarwal, and title is like Quantum Optics. So if we write this, and as soon as we enter in the regime of quantum, in the regime of quantized form, then the Heisenberg uncertainty principle will play. And what is Heisenberg uncertainty principle? This is annihilation operator and this is creation operator, and we have a number operator also. A dagger A. Okay. Using this, and do you know about Hermitian operator? So question is, A and A dagger are Hermitian operator or not? A, just focus on A. A is Hermitian operator or not? Very simple question. Why? This is not eigenvalue. This is the eigen operator. So what is the definition of Hermitian operator? Do you know? Hermitian operator. Hermitian operator means, very simple definition is, suppose we have an operator A. Okay. If its conjugate, okay, and we call it Hermitian conjugate. This is A dagger. If this relation holds, then this operator A is Hermitian operator. Okay, and if this result is not valid, then the operator A is not Hermitian. And what is the physical meaning of Hermitian operator? Yes. So if our operator, we can call it operator or observable. Okay. So if our operator is Hermitian, then its eigenvalue is real. What is the meaning of this? Yes, observable or operator is a physical quantity in quantum mechanics. Okay, so by knowing by defining the operator or observable, and on that observable we can make some kind of measurement. That is, क्योंकि जब तक कि हम कोई मेजरमेंट नहीं करेंगे तो क्वांटम मैकेनिकल वैल्यू भी हम नहीं जानेंगे. ठीक है. तो if we do some observation on the observable, then we can get some outcome, and if that outcome is real, and this is due to the Hermitian nature of our observable. Okay, so the first criteria is operator must be Hermitian, operator or observable, to make some fruitful observation on our quantum mechanical system. Suppose our system, quantum mechanical system is this, and at any moment it's we assign some observable A to make observation on this quantum mechanical system, then we can get some value. Suppose this is A, this is a real number, then we can get some fruitful, some physical conclusion about this quantum mechanical system. Using this, but here problem is that here A and A dagger is not Hermitian. Then we cannot make observation in this notation. To make observation, we can define different observable. Suppose we can define A by using two quadrature operators. Suppose this is x1, x2. Okay, there is some relation. We will not go in detail about that. And similarly, using this, and you can get the expression of k dagger. Okay, so using this, we can get the expression of x1 and x2 in terms of A and k dagger. A and k dagger. And now our observables x1 and x2 are Hermitian, and we can get some fruitful knowledge about our quantum mechanical system when we make observations by using these two operators. Okay, but these two operators are fixed by are bounded by this kind of inequality, that is Heisenberg uncertainty relation. Okay. So by using if we define these two observables x1 and x2, these two observables x1 quadrature operators x1 and x2 must follow the Heisenberg uncertainty relation in quantum mechanics. Now we have signals in different states, and that must satisfy this kind of Heisenberg uncertainty relation for x1 and x2. Using our radiation in classical domain, in classical optics, we can get the knowledge about our outcome up to certain mark. That is limited up to the this is called start noise limit. Okay, and beyond that we can get the error. Okay, or we can get the sensitivity beyond that by using such kind of radiation. This is in terms of quantized radiation. Let us give a brief introduction about this. If our signal in quantum mechanical system is in coherent state. Do you know about coherent state? No. This is a simple depiction of this is suppose our quantum mechanical state is get psi, and here we defined annihilation and creation operators A and A dagger in terms of this relation, and these two quadratures we defined x1 and x2. Here we write P and Q in terms of these relations, and you can see that P and Q are Hermitian. Can you check? P and Q are Hermitian? You should check about that. Okay. So let us skip this. Okay. Coherent state. Suppose this is we denote coherent state in terms of this notation, and coherent state is defined as eigenstate of annihilation operator, that is okay. And for this state coherent state alpha, we can get the knowledge of this Heisenberg uncertainty relation. Like here we have inequality, this is greater than or equal to. So for coherent state we have this equality relation for coherent state. Let us describe in a very simple way. We have quadratures x1 square and x2 square, and this is half for coherent state, and this is the this is the discussion which we are doing at this moment. Now question is that, can we get some relation where, let us describe in pictorial. This is a here are x1
6th floor come fast.
and for this is the vacuum state. Okay, and here we can see that vacuum state is not a point like position in this phase space. If we consider the phase space, then vacuum state can be described by a circle here, originated at origin. Okay, and coherent state. Suppose we apply some operation, and in quantum mechanics, if we do anything, then that can be associated with some kind of operation. Okay. So if we try to this vacuum state to put in phase space at any place, that is meaning that we are displacing the vacuum state in phase space. So let us displace this at any arbitrary position. This is now here. That is, we are applying some kind of displacement operator. That is, if we write this in terms of d alpha, then we have a new state, that is vacuum state displaced by displacement operator, and we have a new state, and this new state is known as state alpha. This is coherent state. Now the relation which we showed here, delta x1 square equal to delta x2 square equal to half, for this coherent state this relation holds. Now our signal at this moment travels in this state if we consider coherent state, yeah, quantized system. But suppose we suppress, and this coherent state have errors in both quadratures same. Okay, now can we enhance the signal quality by some kind of quantum mechanical phenomenon? Answer is yes. Suppose we apply another operation on this circle. Okay, and if we speed this circle at certain direction, suppose we speed this circle, and if you imagine a balloon, and if we speed here, then balloon will be expanded in another direction. So similar phenomenon. So if we speed this circle, suppose we are decreasing the error along certain direction, then error will be increased in another direction simultaneously, and this is due to also the Heisenberg uncertainty relation in quantized phenomena. Okay, so in principle we are applying a certain operation, certain operator on this coherent state to squeeze in certain direction. That is, now we have another state on which we apply certain operator on this coherent state to speed. Suppose we denote this operation by S guide, that is squeezing operator. Then we have a new state. This is squeeze coherent state. Okay, Similarly, we can apply here on vacuum state the same operation, squeezing. That is, we are squeezing error. We are decreasing error along certain direction in phase space to, and simultaneously the error will be increased in another direction in order to follow the Heisenberg uncertainty principle. So here we have another signal, that is vacuum state squeezed by squeezing operator. Squeezing operator, that is squeezed vacuum state. So these squeezed coherent state or squeezed vacuum state are non-classical. Now question is, what is classical and non-classical? Classical means, suppose we consider a photon gun, okay, laser light, laser beam, and in laser beam, photons are emerging for, at a certain rate. Suppose we have 10 photons per second emission rate of certain photon gun, imaginary photon gun, or suppose we have laser beam. This is a kind of photon gun, okay? And why this is so? Because photons are following which kind of statistics? Do you know? No. Bosons are fermions. Photons are bosons or fermions? Bosons. Good. And what is the inherent property of bosons? They are very friendly. Okay? Bosons are living very friendly nature, and they reside in a bunch way. Whenever they reside, they try to reside with each other. They talk with each other, and that is known as, in terms of scientific word, that is bunching. Okay, so whenever bosons will emit from laser source, they will be emitted in a bunched way. Okay, this is a basic property of bosons. And opposite side is fermions. They live like an enemy. They follow certain rule and they don't like to live with each other. Okay, so there is a certain rule to live for the fermions. Okay, so in principle, bosons are emitted, photons are emitted from photon gun, that is laser, in a bunched way. Suppose, for example, we have 10 photons per second, but in modern quantum technological world, this is not good thing. Suppose you are to give a certain source which are emitting, for example, 1 photon per second, and this kind of emission will violate the bosonic nature. That is, the bosonic nature is violating here in your demand, and this demand is termed as non-classical. This is classical, and this is, you cannot explain such kind of phenomenon by using conventional concepts. So now this kind of emission we will call it as anti-bunched. This is bunching. If this is bunching, this is anti-bunching. And anti-bunching phenomenon cannot be explained by our conventional concept of quantum mechanics. So we call this as non-classical state. The quantum mechanical systems in certain state following this bunching phenomenon will be termed as non-classical state and non-classical phenomenon. ये कुछ जो है बड़े ही अब आप लोग सोच रहे होंगे कि हम उलझा दिए हैं, लेकिन एक ढंग से हम केवल फ्लेवर दे रहे हैं, आप लोग इतने देर में नहीं फॉलो कर सकते हैं, लेकिन ये एक तो बुक है, इसमें एक और है बुक, अबे और फॉक्स है, फॉक्स ना, तो फॉक्स की बुक है और C.C. Berry and P.L. Knight, Quantum Optics. These are good books. You can follow and you can learn more things. Similarly, we discussed about the squeezing. This squeezing phenomenon cannot be explained by using conventional concept of optics. So, the state uh, squeezed, the state squeezed is termed as non-classical state. And there are also another kind of phenomena which we call non-classical phenomena. So, to define the non-classical T, we can define different kind of probability distribution functions. In do you know probability? Probability have always positive quantity. Okay, so if we use probabilistic distribution of such kind of phenomenon, that is anti-bunching and squeezing, then suppose we assign some probabilistic distribution, that is this. In our bunching phenomenon or squeezing, coherent state phenomenon, this follows the property of probability. That is, probability must be positive. But there are different phenomena in the regime of quantum optics. What is the meaning of quantum optics? The study of optics with the aid of quantum mechanics is termed as a new field, quantum optics. Okay, so there are phenomena like anti-bunching, squeezing. For that, the probability distribution function E alpha must be negative. Okay, so that is the property of probability distribution function ceases at this moment. In the case of anti-bunching as well as squeezing, there is another phenomenon which is called, suppose if we study the statistics of coherent state, this is like a Poissonian structure. Okay, bell-like structure. So now, if we consider the anti-bunching or squeezing, then this will be synced out. This will be synced out. That is Poissonian. The width of this structure is string. That is called sub-Poissonian structure. So sub-Poissonian photon statistics is also a non-classical phenomenon. Now we go very fast. This is the pictorial description of, this is vacuum state, this is squeezed vacuum, and this is coherent. Here, if we apply the squeezing operator, then we will get squeezed coherent state. This is a quantum mechanical model of beam splitter, which we have used in Michelson interferometer and another kind of advanced version of interferometer. If we consider the classical electromagnetic theory, which we study in BSc level, then if we find out, suppose this is a beam splitter, and suppose this is an electric field, this is E1, and at output, these are two outputs, E2 and E3. And if we don't put anything here, then in classical conventional electromagnetic field, this E1 must be equal to E2 plus E3. Suppose this is energy, this is, so okay. But in quantum mechanics, if we use quantum mechanical structure of this beam splitter, then this relation is not valid. If we use only one input of the beam splitter, then what is the problem? Problem is that we are not considering here the contribution of nothingness. Although this is nothing, but it does play a role. That is, the vacuum state does play the role in this phenomenon. If we consider here, suppose this is current state and this is vacuum state, then the energy conservation will follow. Otherwise, if we are not considering this contribution of nothingness, then nothing does play a role in quantum mechanics. This is the very beautiful property of our quantum mechanics. So here in this picture, we have shown this condition. Okay. Extended by using the beam splitter, we can get the interferometer like this, and this is the mathematical structure, and this is the basic principle of quantum sensing using interferometric technique. As we described earlier, we have now two inputs. This is 1 and 2, and we are using here two beam splitters, B1 and B2, and at this position we have two detectors, measurement techniques, and this detection will follow the quantum mechanical principle, that is quantum measurement technique. So now task is to know some imbalance between these two arms of the interferometer. As we studied about the imbalance between, due to the imbalance between these two arms of Michelson interferometer, to observe experimentally the difference between the distance between two B lines, B1, B2 lines. Here we can find out the unknown parameter phi to know the different signals, to sense the different signals, like in medical purpose, or to detect to sense the gravitational wave or other things. So in general, this is a general mathematical structure of our quantum sensor. There are 3 steps. First step is probe preparation. Here, which kind of state we are using, which kind of signal we are using, this is the first step. And second step is the and first step is known as probe preparation. Second is how our signals travel inside this interferometer. This is another crucial structure. Okay, so and third and most crucial stage is probe readout. If we don't know the outcome of our experiment, then this is irrelevant for us. Okay, so here we have we can use different kind of quantum measurement techniques to know our outcome. Okay, so the basic technique is to sense the some unknown parameter phi. Our task is to exploit these 3 crucial stages to know the unknown parameter phi. Now, problem is that if we do some experiment, there are some errors. Suppose this error in knowing the unknown parameter phi is delta phi. So the task is to minimize this error delta phi. Okay, delta phi अगर 0 है तो फिर हमारा जो सेंसर है वो परफेक्ट है, but there is no perfection. Okay, so there is some kind of error. Task is to minimize this error in estimating the unknown parameter by using these three crucial steps of our interferometric sensing. In this technique, which kind of non-classical states we are using, which kind of structure of our interferometer we are using, and which kind of our quantum measurement technique or detection technique we are using, that may play. But question is that what is the limitation? How much precise we can know about this unknown parameter phi? That is bounded by 1 upon square root f. Here this f is known as Fisher information. That is, you can see, suppose we try to know about the outcome of observable O, certain observable O, that is for the measurement stage, then the relation is delta square phi equal to delta square O divided by this relation, and using this formula we can calculate delta square phi, and the bound up to which we can get the knowledge about the precision of phi or error in phi can be known by using this relation, which is known as, this is Fisher information, and this is known as Kramer-Rao bound. And if we use the quantum mechanical system, then this is termed as QCRB. QCRB tells us about the bound up to which our sensor can work irrespective of the measurement technique. So if we have certain measurement technique, then we can use that measurement technique to find out the outcome, and we can get inference whether our measurement technique is better than your measurement technique or your measurement technique. Okay, so this is the basic thing. And do you know about C.R. Rao? No. आप लोगों को मैं ये सजेस्ट कर रहा हूं कि अपने देश के जो भी स्टालवार्ड्स हैं, आप ये नाम नोट करिए तीनों, और बड़ी ही इंटरेस्टिंग स्टोरीज आपको मिलेंगी। जब आप खाली हुआ करिए, इधर उधर से बढ़िया है कि थोड़ी स्टोरीज पढ़िए। देखिए, C.R. Rao was student of P.C. Mahalanobis. Do you know P.C. Mahalanobis? कोई नहीं जानता? नोट करिए, ये तीनों नाम नोट करिए। पहले हम बड़ा बड़ा काम कर लें, अगर हम अपने घर के बारे में नहीं जानेंगे या अपने जो देश के बारे में नहीं जानेंगे तो फिर थोड़ा सा ब्लैक होगा ये, ठीक है? तो ये नोट करिए ये तीनों नाम। एंड P.C. Mahalanobis also. I am amazing that you are not aware about P.C. Mahalanobis. P.C. Mahalanobis. If you will search about Professor C.R. Rao, then you will get some reference about the P.C. Mahalanobis. Okay, he was famous statistician, and he established about the Indian Statistical Institute, And at one place in Kolkata, Indian Statistical Institute is established, and in other part of India also. Professor C.R. Rao was director of ISI Kolkata, and after retirement, he went to USA to attend her son or girl, and he got the citizenship of USA. And after that, after retirement, he worked a lot, and he got the most prestigious award of science award of USA after retirement, when we like to stay at home. Okay, so you should learn about so by using quantum Kramer-Rao bound in quantum technology, in quantum sensors, we can quantize, we can say that whether our sensor is better than your sensor or your sensor. Okay, so these are some things, and question is that which kind of state will give us most optimal, most nice result outcome for any interferometer. So Professor Jonathan Dowling defined a state. This is termed as N 0 0 N. Okay, this is known as noon state. So noon state gives us very optimal result for the precision, that is maximum precision which we can obtain by using noon state. Okay, so but a problem for this state, this kind of state, is that we here n is number of photons. So if we increase the number of photons or larger numbers, then this state is very fragile, and this is this can decohere very soon as this interacts with environment. So this is the problem, because of which we try to look for another quantum states to find out the enhancement in sensitivity of interferometers. Okay, so there are different schemes which we can. This is the quantum optical measurement. I have don't much time so that we can detail about these results. But if you are interested to learn about this kind of technique, then try to okay, right. This is quantum sensing by Jonathan P. Dowling. Okay, so you should search about this, and Professor Jonathan P. Dowling, his lecture is very interactive, and you will laugh when you will see the video lecture of him, and also you will learn very soon about the quantum sensing technique by using the quantum optical interferometer. Okay, so I suggest all of you to search Jonathan Dowling lecture in YouTube, and I think you will get some nice video about this. Okay, so if you have any question, I am not able to address all things in detail at this moment, but I think that I have ignited some kind of thinking in your mind about this very nice topic, quantum sensing using interferometers. And you can go through the literatures to learn about all these things. And we are doing also some imaging things, and these are my students, and you are most welcome to interact with me at any time. You can send me email, phone me, and you can come here. So you are most welcome. We are organizing a very nice workshop on this topic on 1st and 2nd March, and you are most welcome to attend this. Okay, so if you have any question, then you are more. जब भी जरूरत हो तो हमें मिल सकते हैं, फोन कर सकते हैं, ईमेल करिए.
Okay, thank you, sir, for your precious time. I would like to invite Dr. Sonam Jan to give a token of honor to Dr. Devendra Kumar Misra. Please take a tea break. Yes. Good afternoon to everyone. Our next speaker is Dr. Amritansu Pandey. He has completed his MTech from IIT Roorkee and PhD from IIT BHU. His area of research is optoelectronics, optical communication, 2D semiconductor-based devices. Currently, he is working as Associate Professor at Department of Electronics Engineering, IIT BHU. He is going to deliver a lecture on overview on quantum dots and its application. I would like to invite Dr. Sonam Jain to present a plan to sir. Now I would like to invite Dr. Amritansu Pandey sir to deliver his lecture.
So good afternoon. Audible? Thank you. So let us discuss something different from what you were, let's say, discussing for the last 5 days. It has connection, but we'll see something in different manner. Overview of quantum dots and its application. One thing is common, and that is quantum. So quantum is an issue, and we'll discuss it. This is our institute. We already know. So these are 3 people who got Nobel Prize in 2030, the recent Nobel Prize in chemistry. What they created? They created artificial atoms. Artificial atoms means quantum dots. Artificial atoms means quantum dot. So quantum dot is really getting attention. People are being awarded Nobel Prize. There are applications all around. Few of those we'll see in the next slides, and we'll move. So this is something about the discovery that is there. The question is, why quantum dots? And the importance, the significance of quantum dots. To begin with that, we need to ask certain questions. Are we interested in manipulating atom for certain tasks? Tasks such as storing information into the atom. Like we do store information in different forms. We have pen drive where all these kind of CMOS circuits are involved to store the data. We have other magnetic tapes that store data, but these are not atom level specific things, right? And we know the atoms are very large in number. So if we can manipulate things at atom level, that is going to be the best, right? But the question is, do you have the capability to manipulate at atom level? The answer is simply no. Have you seen the atom? There are microscopes available which basically give us an idea where the atom is located. A blurry picture, a shady picture kind of thing, right? You know, the size of atom is somewhere in nanometer scale, few of nanometer. So still the microscopes that we have, they are not having enough resolution to clearly picture an atom. But there has been a lot of progress. So the point is that atoms are still not in our control. We are not in a position to manipulate. But there are something bigger than the atom that is possibly be controlled. And the quantum dots are like that. So quantum dots are basically a club, a bunch of few atoms, right? We call it 0 dimension. We'll see what those dimensions mean. But this is basically, we are not reaching at atom, so we are stacking in somewhere in intermediate level where bunch of atoms are playing a role. It has very distinct property from the natural world that you see. For example, if you are a student of science, you may be knowing that all the devices are silicon-based devices. Silicon is a bulk material and it has a very different property. If you make a quantum dot out of it, then its properties will be entirely different. Okay, this is how it goes. So there are many things that can be explored around this quantum dot. People are doing it, flexible electronics, sensors, solar cells, and the most important, maybe interesting topic to you people, the quantum communication things, secure quantum communication. So I have organized my talk in different manner, and will not go directly to the quantum dots. We'll start with the requirement of quantum dots or materials like that. That is material evolution from silicon. We'll start with silicon. We are not so insient to discuss about. Then we'll talk about the different type of materials, which is basically nanomaterials. This is again a technology which has evolved ultimately the quantum dots. So we'll talk about different type of nanomaterials that are there. Quantum dot is just an example, right? So although we are discussing beauties of quantum dot today, and then within the quantum dot, its physics, the conceptual thing, that is quantum confinement, the methods of quantum dot synthesis, and the application. Right, applications here are wide, so I have not listed the type of applications here. We'll see in the slides directly. Do you really require something like quantum dots in this world? The answer is really a question. The semiconductor's importance is well known. Now nobody can deny this. Wherever there is a device, any kind of device, then you have semiconductor. You can think of these applications and you cannot think of these applications without semiconductor. So there is a semiconductor all around, and the most common semiconductor is silicon, the popular one, right? The technology has saturated in silicon. We have very good placed VLSI techniques to fabricate all kind of devices, right? The beauty of this fabrication is that we have reached to a limit by reducing the size one by one, to a limit that no further reduction in size possible. So probably now you cannot have IC which will grow something like 1.5 times of the number of transistors per year or something like that. So those kind of limits are there. But silicon is just one example because it is most popular one, so it is noted, others are not noted. So there are other semiconductors as well, 3-5 group, 2-6 groups, and then the nanomaterials come. Silicon has certain beautiful things. Probably if we want to replace silicon, we have to look for those qualities immediately. So mechanically strong, this is the strength. If you see the silicon wafer, you will find that it is very hard. It's easy to purify. Although this statement is little bit vague, I will not say that it is easy, because we have done so much that it is now easy. Initially it was a difficult task. It has a good electrical properties. We are not saying that this is, the electrical properties are best. We already know that there is a good electron mobility and hole mobility associated within the silicon, but silicon has not achieved the best mobility features. For example, it has a band gap which is more suitable, but that doesn't mean that it is suitable for all kind of applications. The silicon is derived from the raw material that is very much available in the nature, and so, and the thing that is not written is that silicon is available in all sort of electrical forms. It has a conductive form like polysilicon, it has a insulator form SiO2 silicon oxide, and it has a semiconductor form, that is pure silicon, doped and undoped. So you have the same base material and you can make different kind of materials out of it. So integration within a IC becomes really very easy. And that has not come directly. People have explored it. So I don't say that this is the achievement that silicon has given. This is the achievement that scientists have got. The problem with the silicon is the whenever it processes with the light. Because my area is area of research and discussion is basically interaction of material with light. So this particular factor is very important for me. So whenever you talk about the silicon and light interaction, then this is very poor. And one consequence of such interaction is your solar cells. Nowadays we have solar cells all around us, but you will find the efficiency of those solar cells is not very high. So roughly 15 to 20% is the highest efficiency that we achieve. So if silicon were good in interacting with the light, probably we might have got 90-95% efficiency, and all the power crisis would have gone. But this is not true. So we have to worry about that particular thing. There is a term known as silicon photonics, which deals with these kind of interactions and provides solutions to it. It is growing like this quantum domain is growing. People are shifting towards silicon photonics to have better interactions because of the establishment. But what I will say that out of these poor interactions, people have devised a mechanism to have relatively better interaction, that is in form of silicon photonics. Then there are materials such as gallium arsenide. We also know that there are many useful properties, especially in terms of light things. They are good. The problem is with the cost. And cost is a huge thing, right? If you want to compete in an environment where somebody is dominating, silicon is dominating, to replace this thing, you require a little bit cheaper device. Otherwise, you will never replace it. So, in fact, technocrats do not think that silicon can be replaced. They can only think that some new applications will come where silicon will not have relevance. That is how it will go. And then we have materials such as oxides and selenides. They also have their beauties and problems associated with it. So these things were basically the kind of materials that were available in the nature directly, right? You just refine it and get it for the work. Then came a new technology which was known as nanotechnology, where people started synthesizing or making materials which is of nanoscale. Right. The beauty of nanoscale in single term is that it has a very distinct property from its bulk counterpart. If you talk about a silicon bar of 1 micrometer length compared to a silicon quantum dot of a few nanometer, the properties are entirely different. One example, for example, is gold. Gold in its crude form looks yellow, right? The gold ring that you see. When you go on reducing its dimensions to the nanoscale, it looks like red. So optical property to say changes. With the dimension, the properties changes, and that is very significant. So nanomaterials are something which are classy, and generally we say that the dimension roughly 100 nanometer is called nanomaterial, although this 100 nanometer is not a very hard boundary. It depends on the environment. So these things may not be visible to you very much, but here you have a macro level, millimeter scale, micrometer scale, and here is a nano scale. So there are many things which do not perform good at millimeter or even at micrometer scale. They start performing very good at the nanometer scale. So there are applications, the things which will work very good. Examples. For example, single walled carbon nanotube. This is what is written here. This is a tube of carbon. Carbon, again, we know is very important. If silicon can be compared to any other material, then I believe that it is carbon that can be compared. Especially for biological things, carbon is better. For any other thing, electronic things, silicon is good. So this is one shape of carbon, right? Carbon in forming a kind of tube, right? The beauty of this tube is that it is the hardest material ever known. This tube, which is of nanometer thickness, its Young modulus is highest in the world. So you cannot break it simply. If you have a long tube of certain kilometers, you may basically create a road which will never break. But this is impossible to create. Even for a centimeter scale of nanotube is very, very, very difficult to manufacture. This is the challenge, right? But the beauty doesn't go fall less if there is a challenge. Then if you compare this with your stand of hair, it's around 10 power 5 times thicker. This hair is 10 power 5 times thicker. And then if you compare, I mean, the ratio is same as hair to your home, the building, right? So you see the size, the nanometer that it incorporates. Now these pictures do not become relevant when you have the system like this. Otherwise, these are the real pictures. Pictures taken of the nanomaterials. You can see some kind of patterns. You see, this is the a crystal pattern. What is name here? Iron platinum nanospheres. This two-dimensional picture. This is a picture where the atoms have been, arranged themselves to be in form of football. Here you have a flower, something like flower shape. The dimensions are in nanoscale. Just remember this thing. Here you have a what you can say that a sugar cube kind of structure. Again, the dimensions are in nanoscale. And here is another kind of structure. So these are the this we call nanoparticle. It do not have a very definite shape, but it is half dimension nano. So if you had a good projector, might be appreciating the things. The point is that there are a variety of materials which basically have nano shape. Only thing is that you have to dig those things. Now we'll come back to quantum dot very soon. So nanomaterials are classified in terms of their dimension. If it is a material which has all three dimensions, which is sufficiently large, then we call it as a 3D material. For example, silicon is a 3D material. If you reduce it in a manner that one of the dimension is very small and other two dimensions are sufficiently large, means you have a micro scale by micro scale thickness sheet, but it has a very thin dimension, then we call it a 2D material. Right? This has been derived from this 3D to 2D. And if it has just one dimension which is significant, other two are less, then this is known as 1D material. If all three dimensions are really very small, this would be very small, again, by mean is that there are few nanometers. Right? If all the three dimensions are few nanometers small, then it becomes zero-dimensional material. And where do you think your quantum dots will fall? Quantum dots are one example of zero-dimensional material. Right? So zero dimension may have a different shape. When we talk quantum dots, we are basically visualizing this material as a single dot kind of scenario, which is basically spherical in nature. Unfortunately, we have all those examples in reality having availability. And you remember, you might be knowing this is fullerene. Fullerene was invented not on the earth, but when scientists brought certain material from moon, then they observed there was a new material. Its composition was complete carbon, but carbon was having different forms on the earth, like diamond was there. And what other form of carbon was there? Graphite was there. Yes, other forms were also present, but this form just first came from the moon. So people observed and they said that this is another way that carbon can be stabilized. Basically, having a shape means having an energy configuration in a manner that it becomes stable. Until unless it is stable, it will break out. So there was a form of this way. There are carbon nanotubes. There are graphene. Basically, all four are graphene carbon forms, and three dimension we have a graphite. So this is how your graphite can be converted into all three forms. So generally, we people work on this kind of scenario where we talk about one layer of graphene. We know graphite is connected layer by van der Waals forces, which are the small forces, and that is how it works. Now again, this slide becomes insignificant when we see a system, but you will find this is mobility curve of different materials. The numbers are rising from low to high, and you see if you go from this set to this set, what I will say, just note this: graphene. The mobility of graphene is highest in all the materials that you see here, and all traditional materials fall somewhere here. They have very little mobility compared to the graphene. So what the mobility thing will guarantee? It will guarantee a fast device operation, right? So if you are making device, it is going to be ultra fast in that sense. Then we have a device structure which has responsibility. For example, photo detectors have responsivity criteria. So if you make device responsivity and response time, then also you will get the highest responsivity and response time. These are the features of photo detectors. This is again highest in case of nanomaterial compared to other material. And next is the strain, that is also good. But we talk limited discussion, and the domain in which we talk about how to make devices out of those materials. The beauty that you are talking about, can we really utilize to make the devices? That is pertinent question. Otherwise, there are many beautiful things. If you cannot realize those things for your purpose, then it is useless. So there are certain things which basically guarantee that the devices can be formed. For example, simple processing, easy fabrication, scalability is ultimate. You can scalability means expanding the domain, right? Heterointegration, two different kind of materials can be combined very easily, and this is very important, especially in terms of devices. For example, this is a plastic material, and this is again a plastic material. If I keep on it, make a device between these two plastic materials and try to use it, it is not going to be useful, because whenever I leave, this is not sticky, it will remove. So these two surfaces are not interacting properly, they are not binding properly, the device is going to be useless device. So those kind of things are really important, and they can be made on flexible, transparent and soft substrates. So it's not necessary that you have a hard substrate device, and definitely there is a revolution going on to make the devices on the flexible substrates, and there are all sort of advantages that is associated, and they can be utilized. So ultimately these nanomaterials are useful nanomaterials. Let's come to the quantum dot, a little bit more about it. So as we defined, this is a zero-dimension material, a nanoparticle nanostructure that exhibits zero-dimensional quantum confinement, which leads to many unique optical. Our quantum confinement we'll see it in the next slide. So idea is that you have a area which is very small in all three dimensions. So if, let's say, a particle, a charged particle is residing in that area, so what your uncertainty principle says, if you know the position of the particle, so the energy cannot be determined, momentum cannot be determined, the momentum and energy are relative. This is the uncertainty principle. So because we are confining the particle in a very narrow domain, so we know little bit precisely about its location. So its energy will become very high. And the consequence of this high energy is that its energy is digitized. So you do not have a continuous energy levels available, but there are only discrete levels that are possible. This particular thing is the reason why quantum dots have very distinct properties compared to any other structure. So you read this, mostly quantum dots are semiconductor, but this statement is mostly only. There are metal quantum dots and useful metal quantum dots in nature, that is well. And there are few set of materials which has been identified to form quantum dots easily compared to other sets. And even today, silicon quantum dots are getting popularity. The beauty is that quantum dots are band gap tunable, because if we are talking with respect to semiconductors. Semiconductors have a band gap. Whenever I say that silicon, then you directly know that 1.1 electron volt is the band gap, right? But when you say that quantum dot of a silicon, then band gap cannot be defined directly. So it depends on the size of quantum dot, not the type of material that you are using. So quantum dots have different varieties which basically govern the principle. So the size is a very important parameter. And in terms of quantum confinement, 1D, 2D, 3D materials, these kind of confinements are quantum balls, quantum wire, and quantum dot. We were calling it quantum wire initially. If it is made of carbon, then we were calling carbon nanotube, whatever way that. So this kind of confinement will lead to the, remember, here is the number 2 nanometer dimension. Basically, I have quoted this number deliberately, not try to fix it exact number, but remember this size. You might be having an idea of Bohr radius, the basic model of an atom that was given by Bohr in classical mechanism, and that was when compared with the quantum mechanics also. So it was kind of, we have a nucleus in which some positive ions are located, and it is surrounded by electrons revolving around it, but location of electron is not fixed because it has a wave nature. So you have an electron cloud around it, right? One electron at a time, and no two electrons are same. So their quantum numbers are different. Their quantum state is different. No two electron can have the same quantum state. At least their spin will be opposite. So they are very well distinguishable. Like we have in class, we have roll numbers associated. No two students are same. Similarly, electrons do also have that. So if the Bohr radius and the dimensions of the quantum dot that you fabricated, they are matching, then only the confinement principle will apply. If the dimension of your quantum dot is very large, so 1000 ml compared to the Bohr radius, then these effects cannot be realized. So it is not that this 2 nanometer is important. This may be having quantum confinement effect or may not be, depending on the Bohr radius of that particular material. Here the material has a role. So what happens due to this confinement? The bands break up, right? And they form energy gap. So generally, whenever the size of quantum dot reduces, the band gaps increase because the confinement is more, so the energy will be higher. Heisenberg. The band gap of a spherical quantum dot is increased from its bulk value by a factor of 1 by r square. Particle's radius that's corresponding to Bohr's radius. This is how it changes. Now, see the effect. This is one quantum dot of certain size, and the same material, the quantum dot of different size. You see their colors are different. Colors can be identified by their emission spectrum, what it is emitting, right? So every atom will have a corresponding signature atom emissions and absorption profile. It will absorb certain wavelengths, it will emit certain wavelengths, and these wavelengths are mostly in visible range because the bonds that is formed has the energy which is of visible range. So that way, if you have a bigger atom quantum dot, then you will find that it is more like a reddish, and as you go on reducing it, it becomes blue shade, right? This is how you see it. These two quantum dots that we are depicting here is made of same material, but their sizes are different, so that has different. So, okay, we'll skip this thing. These are the same thing demonstrated at different level. Okay. Now look at the real pictures, because we have whatever now till now was represented is a diagram. Now you see the real pictures. You see, it is cadmium selenium quantum dots, and you see different size of quantum dots. They have their different colors. Same material, but they are emitting energy. So you can see these are test tubes where the things have been and this is published in a journal. So you will find that this is true in real scenario. The meaning is we are actually able to manipulate material at quantum level. We are not able to manipulate at atom level, but quantum level, quantum dots level, we are able to do that, right? So if you want to have a LED which emits red color, maybe this size of quantum dot is useful. If you want to have a LED which is a purple color, maybe this size of quantum dot is useful. This is how you can identify. Then the ways of synthesizing, obviously the next question will be how to achieve those quantum dots. So there are many methods of doing that. Epitaxial liquid phases, and may not be very much useful at this moment of time, but there are ways, simple ways, inexpensive methods and expensive methods both possible to synthesize. The difference between these expensive and inexpensive methods will be, if say I desire to have a exact this much size of quantum dot, then you have to go for more precise kind of method. If you want to have a just quantum dot of various sizes in the sample, then probably you can use the cheaper methods as well. Again, this is the real image. This is the real image of quantum dot. Scanning electron microscopes. See how the dots have been arranged. The scale you will notice is 200 nanometer. This much is 200 nanometer. So maybe this quantum dot is of 60, 70 nanometer only. Less than 100 nanometer. And this is the two-dimensional surface profile. This is the AFM image. You will find there are ups and downs around it. The size of up and down is basically size of quantum dot. And this is also very ordered. So idea is that there are methods to achieve such kind of things. Another kind of quantum dots are where we coat a material with another material, again in nanoscale dimensions only, by certain synthesis methods, and we achieve these kind of results. The beauty of this cell is important. If you remember, maybe most of us are having nowadays, you may be having TV which is OLED. This is very popular now. So it's a LED TV. OE is for organic LED. So polymer say banai hui LED. That is how you can identify. The beauty of these LEDs are that they are superior to the previous kind of TVs which was made from liquid crystals. They used to illuminate in large area, not so bright. The LED replaced them, and you have definitely a better picture in LED. LED TVs are better. But still, using LED is a device. It has certain dimension, right? Light, if you are making a light emitting arrow, it will have certain dimension. So those dimensions, if you want to talk about the resolution of that TV, so the dimension of this LED will determine the resolution. You cannot look less than that, because either LED will grow or it will be off. There is no third choice in it. So either you will see a illuminated spot or dark spot. So your resolution will be decided by it. And the dimension of LEDs are going to be in some micrometer, few micrometer, that's true. Then this is typically very small. For normal human eye, it is sufficient to differentiate. But if you want to have a quantum based LEDs, which is definitely will come in 2 or 3 years in the market, quantum dot based LEDs, so then the resolution can be even smaller, because the quantum dots have a smaller size, they will illuminate or being off. So the problem with this kind of scenario is that we have seen, if the dots are of not same size, then they may emit different colors. So you will see the change in colors if the size is not controlled properly. So to control the size of quantum dot is a very important issue, and this mechanism somehow serves this purpose. So people have made this kind of codes and structures, so ultimately get the same kind of light. So basically two quantum dots interacting at the surface in a manner that they emit the same light. So here even there is a little bit size change, the interactions guarantee that they will have the similar characteristics. So for that purpose it is important. And these are the methods of fabrication. Let us go ahead. The most interesting task while reading for this presentation, I encountered this. There are people who are not following the electronics or electrical routes of making quantum dots. They are feeding metals to enzymes to create quantum dots, and these quantum dots are really of equal size. So it's a basically biological way of making quantum dots. So enzymes may have a different kind of property, might have been noted. I do not see the research paper actually, but this was something I saw in the. Okay, this is broadly classifying. There are two ways of making quantum dots or any nanomaterial. One is the top-down approach, where we start with a bulk material where the dimensions are all dimensions are high. Then we go on applying methods which reduce the dimension, maybe usko grind karke aise karke, and ultimately end up in getting the nanoparticles and nano-sized particles. So quantum dots can also be synthesized in this route. Another is bottom-up approach, in which we take the compounds which are ingredient of that quantum dot and do chemical reactions. So ultimately reach that dispersion. So properties are little bit different, obviously, because the mechanism followed is different, and even the size distributions are going to be different. So again, if the more precise methods that you use is better. This is something we have done in our laboratory, so that we want to show. This is the method. This method is known as hydrothermal method. We have certain kind of starting materials. We have mixed them to form a Jameson, and ultimately it is hydrothermally activated for a certain time, and you get a quantum dots of MOS2. Right. So we have those things in this method, and this method is for graphene, that is not. And if you see the picture, TEM, transmission electron microscopy, again this is not visible, I believe, from that place, but you see there are two parallel lines that are being indicated. The difference between them is 0.77 nanometer. So these are the dots arranged in this manner. So it is basically a atom there. Not only that, this picture also gives us the idea at what scale we are looking at. Right, the resolution of science, not the human being. This is again a very good topic to discuss about the microscopes. Right, what we can see from naked eye and what we can see from a normal microscope. Even optical signals have a limitation. Beyond that, you cannot see because of its interactions. Then people have formed the electron microscope. Even then, electron microscopes, there are resolution limits. You cannot see electron size less than that of electron. So people have made certain kind of optical changes into it, and microscope is a whole lot of interesting thing to see. So what you see that this is achievable result that we have achieved in our laboratory, and all kind of things. Come back to the applications. Broadly, this is for nanomaterials or quantum dots combined. So this picture was good, so I just copied it. Electrochemical biosensors kind of scenario where you can use a quantum dots or all kind of nanomaterials. Drug and biological systems, these are applications are possible. ये क्या लिखा है? Bioimaging. This is again a huge area where electronics people are very much interested. And then you have a optical biosensors in that sense, optoelectronic devices, electronics, sensors, and photovoltaic. These are the general categories in which certain biological things are there. You'll see the application in better form. So you can have a light emitters and detectors also. You can have quantum dot in computational. So quantum computation is a domain where quantum dots may provide a role. Then photovoltaic devices are there where quantum dots have a role. Targeted drug delivery, this is a very important thing to do because most of the times we talk about the drugs have a side effect, right? How can you reduce the side effect? Do not get them side by side. Allow them to reach only at the place where this is required. So if they say, if you want to kill a cancer cell, target that drug to reach only up to the cancer cell, and it should not affect any other area. So the side effect can be avoided. So how to reach that there? So you need some kind of quantum dot because they are very tiny and strong. You need to have some quantum dot which will be attracted towards that cancer cell. So make that property functional and everything is done. It will reach to that place and ultimately, and if it is not reaching that way, so there is another way. You coat this cancer cell with some kind of interaction. Let's say कि वो उसमें कुछ what we call add some biomolecules into it and add the anti-biomolecule in the drug, and then it will go and attach itself and it will kill that cancer cell. It will not harm other cells. So this targeted drug delivery, it is a lot of people are working on it, and people have been successful in getting the thing. And there are biological application in other sense, that is the spectroscopic sense and other applications. So categorically, there are arrays and microarrays. There are few terms I even do not understand. I have made slide to just to demonstrate those things because this is something very biology, right? Then labeling of the cells means indicating the cells basically. Intercellular structure. You know how DNA, this double helix structure of DNA was invented? Was it a biological scientist who worked or any other person? It was a material scientist who cracked this idea. It was X-ray that did this thing. Some material scientist did the X-ray of DNA and it found that there is this kind of structure, right? Because everything in this nature has it's a signature. We all, people, atom, bond, everything has a signature. If you can identify those signatures, you can always look for its presence anywhere. So techniques are common. Science has a common technique. So that is why things are coming in. Whenever the nanomaterials were invented, they were very useful in biology because most of the sizes of these active elements in biology are of nanometer. So you have enzymes, bacteria, everything, viruses are for nanometer. So people work on those things. Then there are certain imaging techniques. While let's say cells are growing, then those kind of pictures can be done. And we have, if you Google it, you will get a lot of pictures where these kind of things are available. And all those things are possible because of such kind of nano engineering thing. So biologists have little thing to do there. Tagging means identifying certain kind of molecules in that sense, and like cancer cell can be tagged and they can be treated then. At the moment where organic compounds are used to do certain things, I mean those tagging and other imaging and the nanomaterials have certain advantages is because of these things. Like if it is an emitter, if you want to see the presence of cancer cell at first place, you basically allow them to digest some dye which will go and stuck to the cancer cell, and then you take an image, X-ray or ultrasound image, then those things glow and you ultimately get up where the cancer cells are located. This is how but the problem with such kind of dyes are basically they are not fluorescent for all time. So maybe sometime it will fluoresce. Maybe 15 minutes later, if you observe, then you may not be getting the location because that will not fluoresce. When it is nanomaterial of this size, it will always fluoresce. It will never lose its capabilities and qualities. So this kind of things are possible. So there are many things to say this is again a comparison. This cell you already have seen, cadmium selenide with zinc sulfide. So there is a broad and narrow spectrum. This is the common dye that you use, and this is the quantum dot dye that you have. It has a narrow spectra. This has a wider spectra. So it has a significance. Then you see the picture. Again, this is a real picture. It has been copied from a paper. And this is again from a slide from internet. So you see there are three different of cells which are very much visible in a eye, right? Because of the nanoparticles. Because nanoparticles have been introduced, and they have been introduced with different organs, the cells, and their behavior is different at different places. So you will be able to identify those things. So there are possibility. Image the cancer cell in live mouse. This is the image that we predict. If you ask me which one is the cancer cell image, I do not know, because I do not distinguish. My point is a little bit different. So all in all, quantum dots are an attractive alternative for traditional organic dyes, because their quantum yield is large, so they produce light for longer period of time, and you get a better brightness and other things possible. This is again a slide which gives an idea that how the things are moving. So, for example, cadmium sulfide, cadmium selenide, and these are the materials where they emit and absorb light. So you can think of their application corresponding to the requirement. So you have large variety of nanomaterials, quantum dots available, which can work in this domain. Okay, we'll go to next third set of applications. Biology has many applications. I mean, light emitters, LEDs, and as we said that TVs are being formed out of LEDs, and then those LEDs which are traditionally utilizing bulk materials to form a structure, now they are utilizing quantum dots as well, right? So quantum dot LEDs are efficient, they are more kind of bright, they have more directional pattern. So you can see, for example, quantum dot LED at 270 degree of angle without any problem. There will not be any image crisis. Things like that has been, and gallium nitride is the most sought material in this domain. But there are people who are making organic LEDs, quantum dots, and those things. The matter of interest for you is computing, and here we have certain conflict as well. Like electrons have their limitations in doing manipulations. That's why we are talking about replacing this Boolean logic systems by another kind of system, and quantum computing is one such thing, right? You talked that we will be using quantum parameters to manipulate data, to do all kind of gated operations, memories, and everything. But there are other aspects also. Before reaching to quantum, you have a light, which can also behave much better way than the electron is behaving. So you have a photonic computers before the quantum computers in practice. Photonic computer, if it has to be realized, then silicon photonics is one such domain that interactions are good. And for that you require quantum dots. There is no other material, because at atom level you will not be in position to manipulate the optical properties. Quantum dots are such that you can manipulate. So quantum dots are basically intermediate junctions where most probably we will be able to have the photonic computers possible. I do not know who will win the race. It seems that quantums are winning, but it is not sure. But photonics do have its applications, and thanks to quantum dot that they are playing role. But the chapter do not end here. We have the applications of quantum dots in quantum computation only. So the point is, let's see this next slide. We have an idea of spin qubits. So you always talk in terms of qubits in that scenario. So if it is a, let's say a quantum dot which is of sufficiently small size and you have one electron trapped into it, so you can use as a qubit. So either a single electron spin or multiple electron spin in a quantum dot, depending on if you can utilize this thing, then probably you can make quantum computation at this scale also. At least memory is very feasible, right? You can have a memory kind of thing. So there are issues which is in this domain, like it is a solid state quantum information processing system because quantum dots are solid state things. So once it is a solid state, then it is very much easy to control and scale. For any other systems, the controlling is a difficult task. And it is historically also in silicon devices, we have been doing this thing very efficiently. So that is one great advantage. And if it is a semiconductor qubit, spin qubit you are talking about, then magnetic and electric field controls are possible. You know, band gaps and the other things can be tuned. So by applying its electric field and magnetic field, both way you can manipulate. This option is not available for all kind of things. There are issues with the noise, means that can be tolerated because there will be bound to have certain noise things, and spin interaction with the band structure, they play important role. So these are certain bottlenecks that must be avoided to have a realizable form. So there are three pertinent questions that is asked if you want to have a spin. There are papers around this spin qubit based computing. People are basically trying to create logic gates, memories out of it. At least theoretically, people have done it. What physical property of quantum dot can be used to carry the quantum information? That is one question that is being asked. How do you create quantum gates using this system? Because this is only we can be manipulating the things. And how to create simple quantum circuits out of it. If we can solve these questions in a proper manner, let's say, then probably we can use quantum dots as a element to do the quantum computation. Because quantum dot manufacturing is easy, we know the synthesis process, which is good, so we can have those kind of things. And the associated things that, I mean, in great detail goes this excitant system. Excitant means when there is a light and electron hole pairs are generated, they are basically coupled electron hole pair, they are not completely independent. And electron spin and nuclear spin, those things need to be counted. Then you can have this kind of. Other set of application of quantum dot, which is most popular after biological thing, is the photovoltaic devices. People are trying to increase the efficiency of solar cells and devices, and there is an ultimate limit. You are not able to do that very efficiently. Either the processes are going to be very costly or the technology is not viable. So that way we have much better systems. Now we are saying that the photovoltaic cells can be realized on a flexible substrate. Even your cloth can have this kind of, you may be producing electricity someday by this mechanism, and quantum dot itself are going to be more interactive towards light, so they will be efficient, and that will also improve the efficiency, and there are many ways of doing that way. This is the targeted drug delivery system that we talked about. There are certain cells which are affected, so that your drug will go and bind that affected. The carrier is going to be quantum dot. So quantum dot has a carrier in that system. There are certain conspiracy theories around this also. People say that you are introducing quantum dot in the body, which is very sharp, they are very standing, you cannot kill them, that cannot be flushed out very easily, but that will ultimately affect your health system. But those things are later part, maybe you will end up in getting some kind of regulation, but at least it is possible that let's say you want to attach the drug to this cell, the red cell only, so you can use quantum dot as a carrier to reach that value. So numerous certain applications are there. अच्छा ये तो हम छोड़ देते हैं. Let us skip this thing. This is again one cell that has been realized, published in a paper. So you will see that the two different set of quantum dot, and they have realized a better power conversion efficiency. In one case, it is very good. Again, this is for picture only. So you see there are TiO2 nano, TiO2 rods, and that has been, synthesized by this CDs area. We call it sensitized. This is just a term. So basically they are interacting. So you have a rod around it. This is wrapped in a fashion. And you see these are the rods. Again, at 5 microscale, you see a Himalayan cloud. At 500 nanoscale, you see that these are very sharp and very clear images. You could draw. So you have a variety of size and correspondingly variety of color. So this is the reality. Again, I'll show you one example that we did in our lab about the optical detection, where we fabricated MOS2 quantum dots with the effect of graphene, and we found a very peculiar result. Where is that? I'm not going to. The result was quite interesting in the sense when there was no light, then this red curve was representing the current. So there was a current in the device. You bias your device, photo detector, and you achieve that. When you incident a light, visible light, then current was reducing. Generally, the effects are just opposite to that. Right. Whenever light is incident, extra electron hole pairs are generated and it increased the current. But here we observed that there was a problem that is there, and it was because of the MOS2 quantum dot and graphene system that we realized. There was a reason behind it. We called it a poly-blocking phenomena. This phenomena was observed. So, we reported it was a very good observation that we did. Again, this is a different set of experiment that we are doing. I'm showing the examples of light for photo detectors. Now, come to another property in terms of devices that are being realized with the dots, quantum dots. If you compare the two important characteristics, responsivity and response time, this time is large and this time is small. This is 10 power minus 8, right? So being this is 0, 10 power 2, 10 power 4, 10 power, that way it goes. So you will find that most of the quantum dots are very good in all sort of scenarios. Here you have a graphene, here silicon photodetector. These are comparable, but these things are really better. So thank you. I have not gone into details because the time do not permit us, but there are definitely interesting applications of quantum dot, and it is not explored fully. Biologically, I agree that there are many investigations. Photo detectors are being investigated, but other applications they need attention. So thank you very much for listening. If you have any question, please.
Thank you so much, sir, for your precious time. I would like to invite Dr. Sonam Jain to present a token of honor to Dr. Amritanshu Pandey, sir.
So guys, this is the end of our session of this short-term course on Introduction to Quantum Communication and Machine Learning. And in this ending session, I just want to thank everyone, especially the participants, online participants, as well as the offline participants for participating in this short-term course. And I hope you guys have got some good ideas. And thank you so much for your time and your patience and for all the inputs and the questions that you have asked, because those questions will also help us in improving faculties as well. So thank you so much for your time, and a huge round of applause to all of you. So now we'll go for the certificates distribution. I'll just call upon the name, and please come and take your certificates. And for the online candidates, their certificates will be sent to their mail. Thank you, everyone. Please, we'll now have this certificate distribution.
Abhimanyu Kumar Gaud, Abhishek Maurya, Jasnesh Kaur, Viranjan Kumar, Anant Tyagi, Mridul Sharma,
Give him a use number.
Mridul Sharma, Manan Malik, Swarnedu Naskar, Purnendu Seat, Kuldeep Kumar Srivastav,
Please take your own certificate.
Kuldeep Kumar Srivastav, Kartikeya Chadda, Shivam Kumar, Shiv Shekhar Misra, Abhay Rai, Avinav Vardhaman, Allam Setti Sai Krishna, Manav Kumar Jalan, Pratibha Rana, Avneet Singh, Siddharth Rana, Chetan Tiwari, Harsiya Joshi, Shikhar Madi Tripathi, Ritesh Kumar, J. Himangana Shai, Anubhav Misra, Vishal Tamoli, Nitin Kumar Rajvanshi, प्रथम केसरी, लक्ष्य, अर्पण गौतम, विशाल कुमार, प्रणव चौधरी, कुमार गौरव, अनिरुद्ध, शोएब अख्तर, गौरव सिंह, गौरव सिंह रोखा खेतरी, अंशुमान निवास, विकास कुमार चौहान, मानस पटेल, हर्षिता राजपूत, शिवम पोसवाल, प्रीतम दास, हर्षिता, आयुष खन्ना, मिंटू कुमार, चिन्मय केसरी, मिंटू, चिन्मय केसरी, निशांत सिंह, मनजोत सिंह गिल, श्रीवास्तव प्रियांशु, काशवी अग्रवाल, सक्षम गुप्ता, हर्षित गुप्ता, हिमांशु कुमार, आभास सिंह, ऋतिक रोशन त्रिपाठी, टीएस गुरु राजा, कबीर मल्होत्रा, एकता तनवल, अमन तिवारी, ईश्वर साई तेजा, अनीस उद्धव, केएम श्वेता, थॉमस जे, शिवम यादव, वृंदा मार्कंड, एबी जॉन, श्रेया बासुराय, रिया, हर्षिता, शिवांश मिश्रा, प्रज्वल वाजपेयी, विवेक कुमार, मोहित जोशी, अभिज्ञान, कृष्णा किशोर, अविनाश मंडल, आर्यन प्रताप श्रीवास्तव, राजीव कुमार, विभूति गुप्ता, अवनीश वर्मा, मुस्कान जिंदल।
Anyone who is here and has not got the certificate, please come to them. We'll search your name. Please come one by one. Remaining papers. कुछ मुझे दे दीजिए, कुछ आप दे दीजिए. So I'm just calling out the. Please go back to your seat. I'm just calling out the
वहाँ
name.
पे
And if you are here, then you can come. Muskan, Vibhuti Gupta, Rajiv Kumar, Aryan Gupta, Avinash,
आपका नाम नहीं है?
Krishna Kishore,
बोला ही
Vivek
नहीं।
Kumar, Prajwal Vajpayee, Harshita, Shreya, Vrunda, Shivam Yadav, Thomas, K.M. Shweta, T. Ishwar, Aman Tiwari, Ritik Roshan Tripathi, Abbas Singh.
नहीं है आपको। आपका नाम नहीं। नहीं बोल दो उसी को लेने। आपका नाम अनाउंस नहीं हुआ इसमें? नाम आया था
शुरू में आया था सर, स्टार्टिंग में। इसके बाद मेरे साथ
इसमें नहीं है लोग नाम?
नहीं।
अच्छा,
निरंजन हमारे साथ में था कार्तिक।
हाँ, उन्हीं के।